Good morning, everybody. Thank you for being here. And this is another seminar by the Instituto de Astrofísica de Andalucía. And today we will have the talk by Dr. Teresa Wiegert. And she's in-house. She will talk about radio continuum halos in nearby galaxies and the CHANG-ES project. So Teresa is currently working here at the Instituto de Astrofísica de Andalucía, and he's doing a postdoctoral contract for Lourdes Verdes Montenegro. The duties are twofold: work as a liaison between the Spanish astronomical community and the immensely interesting Square Kilometer Array, the world's coolest radio observatory. As well as she's doing own research together with the team at the Institute. Currently, she's involved with the next data release for the C configuration observations. For the first and second data release, B and B configurations, see the CHANG-ES website, please. And she's also doing some work, instrumental work, in getting new S-band observations of the CHANG-ES galaxy observed in summer in 2021. And after that, she will talk, I think, about these new results. So thank you, Teresa, for this seminar. The floor is yours.
Okay, thank you, everyone. It's actually more people that showed up than I expected, because it was a short notice, and I had to cancel a few times because my son got sick, and you know how it is. But I'm really excited to be talking to you about this. And a full disclosure, I volunteered to do this talk because I'm going to do a shorter version of the talk at the EAS, and I like to be prepared in advance. And there's no way I'm going to do that unless I'm forcing myself by a situation like this. So this project has been going on for about 10 years now.
Sorry, you need to share the screen for the Zoom.
Oh my goodness. How do I do this?
In the Zoom.
Okay, I'm going to have to go out here. Zoom, share. I think it's this one. Okay, it's working?
Yeah.
Perfect. Okay. So yeah, you may be thinking that this is old stuff, but it's not. It's been ongoing for a long time, and I need to go through the background a little bit to show you the coolness of the current work. And here is the outline of the talk. So I'll go into a little bit of background first. A lightweight crash course on the continuum data. What is it and what is it useful for? And then a little bit of VLA history, because the change of VLA is what made this project come forth. And then the science questions that led to the project. The observations that were a lot. Actually, these observations are really the reason to why I ended up becoming a bit of a VLA crazy person, or the person everyone asks when they want to have VLA observations in their data, or things like that. And this is something I don't mind at all, because I just love it, because there were lots of observations. There are a number of data releases, and then I'll go through a few of the highlights of discoveries, things that we expected and things that we did not expect, and the continuation. And some first peeks of the new results from these S-band data that I will go into. This is what we're calling CHANG-ES 2, by the way, but it's not an official name just yet. And there is some bonus slides too, if we have time for it, and I hope so. So, radio continuum emission. So in any gas, which has free charged particles, electrons, lots of particles, lots of accelerations, and there will be many time scales involved, that gives rise to emission at many frequencies, and this is how you get your continuum. A continuous spectrum that is broadband. And emission at some frequencies are more probable than others, so you can get this characteristic spectral shape of your continuum emission. Now, in Continuum, there are two different contributions, and there is the contribution from thermal emission. And what happens here is that you have a charged particle, for example, an electron, that is deflected by another charged particle, a proton, and loses energy when it's decelerating. And this can happen depending on the energy, you can have photons on many different wavelengths. And this is called Bremsstrahlung. It's also called free emission or thermal emission. Actually, Bremsstrahlung, there may be other thermal emissions than just Bremsstrahlung, but in radio, this is the prevalent one. And it takes place in H2 regions and diffuse ionized gas. And the main thing to think about here is that the particles causing it are non-relativistic. And then we have the non-thermal emission. And the main big difference here is that it's really a similar situation, but we have a relativistic particle in this case. And instead of being deflected by an E field around the proton, it's being deflected by a B field, a magnetic field, and starts spiraling around the magnetic field line, and thereby sending out emission as it's decelerated or it's changing acceleration. And so because it's so similar, you can also call synchrotron radiation Magneto-Bremsstrahlung, I think. Something with Brems at least, because they are related, even though they are different. And one thing you should know here is that you cannot have synchrotron radiation without magnetic fields being present. Okay, so this is your indicator of your existing magnetic fields. And the image I have there is actually synchrotron radiation in a jet of M87 in the blue. They can also show up in pulsars, in supernova remnants, and radio galaxies, and certain quasars. Now the question is, if you have a galaxy and you detect the magnetic field there, how do the electrons get out into the halo? Okay. Oh, and I want to point this out as well, the spectral behavior. To the left, you have Bremsstrahlung, so thermal emission. Here it is. And you will always have a flat, in the radio regime, you will always have a flat or slightly positive spectral response here. This one actually also cuts down, as soon as it goes down into optically thick region, it will cut down as well, but it's off the scale. And for example, in radiation, while for synchrotron emission, this is called the spectral index that I'm saying here, by the way, the shape of the curve. So here, the spectral index is negative. This is actual data for Cassiopeia and different examples of the synchrotron spectrum. And it's the spectral index here, which we call alpha, and I will talk about this later, this is why I'm not doing this now, is typically from minus 0.5 to minus 1.5. And if you have this curve indicated in your spectrum, you will know that you have magnetic fields. In radio, it's quite nice. There is quite nice simplifications for thermal gas, by the way, because we are in the Rayleigh-Jeans approximation of the Planck curve. So it makes for easier calculations. Anyways, the next background thing I want to do is talk a little bit about VLA. So what happened was that we had the old VLA and it needed to be upgraded. And because it got upgraded, it also became a pathfinder for the SKA. And this happened well, it took place during many years, but it was finally finished in 2012. And with the new VLA, there were fiber optics instead of all the waveguides. There was a new brain computer correlator, which was built in Canada, by the way, called WIDAR. And as the name indicates, wideband, the new VLA would have a much better sensitivity in the measurements because of a much larger bandwidth. Sensitivity goes with bandwidths like this. So the measurements you could take would become an order of magnitude more sensitive. So, and there are also a few side effects, and I put a line over these because they aren't really so important anymore. Larger data sets, of course, but we also have better computers, longer reduction time, same thing, more RFI, definitely, some previously unknown, yes, but not anymore because now we learned about them. During the 10+ years that has taken place since this time. So what can we do? What could we do with the new VLA? And there were ideas galore. I will talk more about this particular image a little bit later, but here it serves as an illustration. So meanwhile, as this was going on, there were all these science questions that we wanted to answer. And now finally we had a means of doing it. And we needed this sensitivity that a VLA would bring along because we were interested in the halo. And I need to point out that when I'm talking about a halo here, this is not dark matter halos. This is halos of gas and the continuum emission, and they're not related. So the questions came up like this: what is the nature and origin of radio halos? And we were wondering, what is the prevalence of radio halos in spiral galaxies? What are the physical properties of the extraplanar halo matter? What happens at the interface between the disk and the halo that causes the halo to look like what it does? How do star formation rates and other activities in the disk affect the halo? Are they the main reason to why we have a halo? Or are there other things? How do galaxy environments affect the halo? And then we go into, are there any extraplanar phenomena that could be attributed to intergalactic medium accretion? And then we go into the magnetic fields questions. What is the origin of galactic magnetic fields? Because we knew they existed. There just wasn't very good observations of them as yet, very deep ones. And how does, for example, Faraday rotation affect them? How do magnetic fields and cosmic rays and their mode of transport and wind speed affect the dynamics of extraplanar matter? And there were other questions. What about the far infrared radio continuum correlation? Cosmic ray transport and high energy modeling? What about the difference? What can we see in the disks and the nuclei when we go much deeper than we have before? Lots of questions. And so we had lots of science goals, this group of people that got together, and they wanted to look at the origin of halos, the physical conditions, see how it was really related to star formation rates. But what are the correlations? They're not obvious. What are the role of companions? And here is a sketch of disk activity that may affect the halo. There are outflows here via galactic fountains. There is inflow from the IGM. So supernova explosions in the disk here, these red thingies, can break through the galactic disk and inject hot gas into a galactic corona, perhaps driving a galactic fountain wherein the gas cools and condenses and eventually recycles matter into the galactic disk. So what is the cosmic ray catalyst? Can it be Parker instabilities? And how far do the halos extend really? Oops. There we go. And I snitched this this slide last second from the PI of the project, Judith Irwin. So, and here I just want to point out the following: that star formation, the galactic fountains caused by supernova explosions, etc. It's not the whole story, because you will have galaxies with low star formation rates, and they still display halos. So are there, and photoionization from star formation regions alone would be insufficient to explain excitation of the diffuse ionized gas. So there is another source of heating needed: shocks, magnetic reconnection. What can it be? environmental effects, inflows, interactions, which here, I don't know if you can see it in the bottom, there is a need for the measurement of the magnetic fields and observations of many galaxies. Okay. So what do we need? We need observations of many edge-on galaxies. Edge-on because then you will be able to see the halo better than in any other other situation of galaxy in the sky. The halo intensity is about 1/10 of the intensity of the disk. So you need really faint, really good sensitivity of your observatory. And the polarization in its turn is about 1/10 on the halo. And we were looking for wideband continuum observations in different frequency bands, as wideband as possible, different resolutions to see both the large scale structures and the small details. We want to have polarization, so we wanted to measure in all Stokes polarization products. It might not be enough with an array, because if you don't fill in the gap properly, you don't have enough time, you will have you won't have the large scale emissions. So combine with single dish antennas, and in our case we use GBT and FSBR for some of our galaxy, not all of them, and other data. So this turned out to be a symbiotic project between CHANG-ES, the project name, and NRAO, who runs the VLA. Symbiotic in the sense that NRAO gave us all this time to do these observations, to test out a new telescope and see how it could, what we needed. What did we need in terms of data reduction stuff? What did we need in task for CASA, the program that we were using for calibrations? Would there be errors? So it was a big test project. And for us, it was really great because we got this huge bandwidth. Now, CHANG-ES stands for Continuum Halos of Nearby Galaxies and EVLA Survey. And the telescope was dedicated in 2012, and as you know, it's called the Karl G Jansky Very Large Array. So it made our acronym a bit tricky. For future reference, it's good to pick a word that is doesn't mean anything at all, or everything at all at once when you do a search on it. So like CHANG-ES, you can just search on it, and perhaps make sure the telescope name you're using won't be rendered obsolete later on. So here is the consortium as it was in 2013, and I'm really sorry I don't have a more recent picture, but it just doesn't exist. In here we have a lot of countries represented, and there is X-ray people, Gentao, Daniel. There is theorists, a number of them. I can see it on here. Oh, where is he? Oh, he's doing canoe here. Richard and Andy, and there's lots of Germans because they are good at magnetic fields. Many grad students and others have joined after the fact. So this group is actually about 30 to 40% bigger, and some have fallen off. And now we have a new team that is interested in new S-band data that I will talk about later. And so they're not in here, but I would like to point out the original PI, Judith Irwin of Queen's University, and the current interim PI, Volker Hiesen, from Hamburg University. And he is the person behind the cosmic ray transport modeling code that we have applied a lot on our data, but it's called Spinnaker. And here's our logotype. These are the 35 galaxies in the sample, and they're all, the orientation on the sky here is the correct one. They have not been tilted or anything like that. Okay, so the sample, we needed observations of many galaxies. There was a limit to how much galaxies we could fit in with the sensitivity we wanted, but we ended up with 35 galaxies. They needed to be sufficiently inclined so we could see the halo, not too big of a declination so that the VLA could still observe them. The further south they go, the more elongated your resolution element will be, which is not as useful for comparisons anymore. They needed to be of a certain size, big enough for good enough resolution, but not too big because then you needed too many pointings, and strong enough. And there were a few exceptions here because people in the team had their favorite galaxies they wanted to look at. So this one is a little bit too large and too faint. This one is a little bit too large, and this one is a little bit too small. But in the end, we ended up with varying morphology, varying nuclear activity, environment, halo extent, and some we did not know if they had halos or not. Most we did not know. And here is the data. They were observed during 2010 to 2013 and 406 hours. And I don't know how many, about 100 more hours in S-band than just the previous 2 years. We used 3 EVLA array configurations, B, C, and D, which means 3 different kinds of largest baseline and resolutions and intensity. In 3 bands, the original observations were in L band, which is centered at 20 centimeter, 1.4 gigahertz. This we did in all 3 configurations of the 4, there's A as well. And C band, 6 centimeters or 6 gigahertz, 5 gigahertz. And then we added on changes to in S band at 3 gigahertz. All polarization products. These are the resolutions and the RMS noise, so the sensitivity is down to 3 microJansky per beam, which is really good. And as an example or a comparison here, if this is an order of magnitude better sensitivity, depending on configuration, compared to previous surveys that were around 100 or up to 90, 45 to 90 microJansky per beam. And for those of you who are not entirely familiar with EVLA, and this is soon going to be obsolete as well within the next 10 to 20 years because the NG-EVLA is being built. So this is soon going to be trivia, but I still wanted to mention it because it's cool. These are the different array configurations that we used. D configuration is has the longest baseline of 1.03 kilometers, and it's tight. And so this is a bit more details than you needed, but here we have to be aware of shadowing for the low declination galaxies because the antennas are tight together. C configuration is a really good compromise between intensity, sensitivity, and resolution. So that's the only configuration we use for S-band actually. Longest baseline 3 kilometers. And we did 3 hours per galaxy C-band. So this is the most of our hours in 39 scheduling blocks, just to give you an idea of the fair amount of work that goes into setting up these observations. It's really like playing Tetris with all the parameters you need to do. And the B configuration looks a bit like this. So I am giving you this image instead of myself standing next to the L-band horn of one of the EVLA antennas, which is pretty big. Okay. And there is a configuration we actually used as well for separate, excuse me. Yeah. Excuse me. That's the longest baseline. And one of the CHANG-ES members, Yang, she was applying for a configuration to look at low luminosity AGN and nuclear ring of one of the CHANG-ES galaxies. Now, the most exciting thing of all, and the most time-consuming, which never really is reflected in your publications, is the data reductions. But I'll spare you this in the seminar because the results are really more interesting for you guys. And just mention the software, which is CASA. And it's very useful and has been in the beginning, I was a user and a tester of this and was driving a few of the developments, which I feel really happy about. And currently CASA is on the version 6.5 point something. And when I started, it was at 3.4. So there has been a lot of developments over the years. So what we are using it for is multi-frequency imaging, bring out in-band spectral indices, bring out depolarization. Actually, rotation measure synthesis, you use CASA a bit for, you create data cubes, but then you use other tools for it, and lots of other goodies. And I'm still talking about the data here. So we have this website called at queensu.ca/changes. And there, all our galaxies are shown. And if you click on them And I'm going to be using NGC 3044 a lot throughout the rest of this talk. You will get another page with data that is available, which is not entirely true. The deconfiguration data is available, the B is available, and then we have other data releases, polarization images. The C is not available. It exists because I prepared it, but it has not been published yet. So if anyone wants to see configuration data, you have to talk to me. And during the years, there's been problems. They discovered at the VLA that the primary beam was properly shown or given in the right setup. So we needed to correct all our data products after the fact for the correct primary beam, including all the spectral index maps, which took a little bit of time. Anyways, so if you click one of the galaxies, NGC 3044 here, here are your data products. Total intensity, linear polarization, polarization angle, spectral index, and the spectral index error. And all of these are FITS files. You can just download directly. So they're not very big. And it's easy access to the data that we have. If you want to have the raw data, you have to talk to someone in the consortium or the steps that led up to these. Okay. So now I wanted to show you a little bit of snapshots of the data that are available and point out a few items of interest. This went into the first data release paper of the deconfiguration data. And there are two resolutions. We have Briggs robust 0, and then we have a smoothed by UV tapering to about double the beam in resolution to bring out the fainter emission for 2 bands. Let's see. I'm a little bit confused here what I'm seeing here versus here. I'm not sure. Anyways, we have C band and L band in this one. We have the B vectors here. Notice here how they are kind of X-shaped. We'll talk about that later as well. The spectral index maps. This is in C band and L band. And the error maps. This is one of the more interesting parts here. It's my PhD supervisor, J.N. English. She is also an artist. So she is partly in charge of most of the images that come out of this project that are more artsy, but still keeping the science. So this is an image that attempts to show the extent of the halo by overlaying the different bands on top of each other. Okay. And here is data release 3. This is all the deconfiguration data. I mentioned the spectral index map here because this is the in-band spectral index, and we had a little bit of difficulty, you can see here on the error maps, with trusting these spectral indices initially, and a lot of work went into making sure, pointing out how to make them reliable, in essence. So in this one, we did not do in-band spectral index, but went from the L band in the B configuration to the C band in the C configuration, and band-to-band spectral indices are the ones that are shown here. So I mentioned data releases. There are 4 so far. The first one are the deconfiguration data. And it includes as well, what happened here? Flux densities, star formation rates, and then spectral indices. Then, in order to do something called thermal, non-thermal separation of the continuum emission, we needed H-alpha images. And so that's the second data release. New star formation rates, and this is by Carlos Vargas. Then came the rest of the second part of the B configuration of the changes observations in B configuration. And here we looked into the AGNs a little bit more. Remember, in the configuration, you are a lot more detailed, and so you get a lot more information about what's going on in point sources. So we will be able to detect AGNs. And we also had a group of CHANG-ES members who were interested, even though continuum observations with the VLA does not give the kind of channel resolution you would want to have for spectral observations, unlike SPA, for instance, where you can get the continuum as a byproduct of the spectral observations. They were still able to pinpoint the H1 line in our LBAN data and make cubes and make moment maps. So we have an H1 imaging data release based on these continuum data, which I think was quite impressive. Now, these, I don't know if you've been reading these titles, but they, to me, sound really exciting and interesting. So this serves as a good segue into the next session, which is on the data results, the results we've seen. What have you learned from this? But before I go there, I just need to say that we also have the C configuration data and the S-band data upcoming as data releases. This is a messy slide, and I won't go through all of this right now, but just wanted to point out that on the CHANG-ES website, there's CHANG-ES publications, and this, as you can see down here, started 2019, and it goes up to 30, CHANG-ES 30, yeah. So there is a lot more down here in terms of papers that came out. And they're also related, unnumbered theoretical papers from our in-house theorists. Actually, I want to mention a few things here. We have 4 press releases, the 4 data releases. There are some unexpected and some expected results, some never seen before in any galaxy. They are in these discrete features. There are disc halo structures, sometimes only seen in polarization. More on that shortly. Broad scale halos with reversing magnetic fields and tidal reception events, and much more. Okay. So the main result from data release 1, or one of the main results, is the extended halo that we see in this image. This is not just a painted impressionist picture, but it is a stacking of all the halos of all the radio emission for 30 of the galaxies. We had to exclude a few because some of them were too distorted because of being in merger or having a very strong plume and bubble, and some of them were too distant. The resolution beam was just too large to use them. So we excluded 4. And the result was this quite astonishing extent of a halo. So this is the median halo of the galaxies in our sample. And it serves as a confirmation of a prediction in 1961 in a paper called Origin of Cosmic Rays, that galaxy halos extend to large radii above and below the disk, but not seen before. And the optical image in the center here is just a representative of the galaxies that include. So they were all oriented in the same way and scaled to the same size in order to be able to be stacked like this. And this is a Hubble image of NGC 5775 galaxy in our sample. And so what we could see as well by looking at the individual galaxies is that halos of gas and cosmic rays in magnetic fields are more common than previously thought. And this was kind of unexpected. The larger halos tend to have higher star formation rate density. Sorry. Now, there is a fair amount of people here at the institutes that are interested in AGN. So I thought it would be cool to include some of our not initially sought after results on AGN. That was not part of our questions, but AGN are quite hard to ignore. Initially, because there were severe problems in cleaning the radio. When you go from radio signal to your images, you deconvolve in a process called cleaning, and This can be more or less tricky depending on how high dynamic range you have. You can't really see it here, but this is NGC 660, and there are lots in the contours here. There are lots of spikes radiating out from the central AGN here. So the stronger AGN you have in one of your radio data, you will have a harder time getting a good image out of it. You can succeed though. We did, for instance, with some Nearby Galaxy that I failed to put in here, but it requires a little bit of trickery. And everywhere in the field around, these dudes showed up with little double beams, such a strong radio source with two lobes stretching out of it. And it's also hard to ignore because it's so darn interesting. And so we started looking into, and this is an example of that actually. This is one of the sample galaxies, UGC 10288. And this guy should not even have been included in our sample because the galaxy itself is way too faint, but no one had ever seen that the brightness you measured from it actually was from a really strong background double lobe source sitting in the background there. And here it shows the radio data. This is optical and H alpha, I believe. But as you can see in the radio data, you can barely even see the little galaxy. So it shouldn't have been included. However, we could learn a lot of things by looking at the emission that was coming through on the backside. So there's a whole paper dedicated to this galaxy. And we also, another paper dedicated to a catalog of all the AGN sources that we found in the fields of our data. And then there are hidden AGN that don't show up except for in polarization. So we don't see these lobes in intensity, in normal continuum intensity. And then we take out the Q and U images, we make the B fields, we make the polarization intensity map. And this is the center of the galaxy. The contours here are the Stokes high intensity. And as you can see, it's kind of hidden. But then the polarization lobe shows that there are some kind of lobes here by the way they are oriented. And as well, you look at the spectral index maps, and you find that there is a conspicuously flat spectral index in the center of the galaxy, indicating that there is an AGN. So we adopted a bunch of criteria for how to detect an AGN in radio continuum. Point-like cores that are very bright, making it hard to clean your data. Too high luminosity to be caused by a collection of supernovae. Flat or positive spectral index in the center, bipolar or lobe-like structures, variable with time, and I'll go into that in the next slide, and circular polarization. This is incredibly weak polarization to detect, but we did for a bunch of galaxies. Okay, so tidal disruption events. So a really cool example here is NGC 4845. We have data that is spanning about half a year. And the first ones are really hard to clean because of the strong AGN in the center. But then it got weaker and it was easier to clean. And we noticed that it's decreasing in intensity. This was a serendipitous discovery about a year after hard X-ray outbursts, supposedly or potentially caused by a super Jupiter object getting too close to the central black hole. So what we had was 5 data points during a 6 months range, and these were varying with time, declining intensity. And because we discovered this, we also asked for new observations from the EVLA 3 and 4 years after, and were able to plot our data points. And the later observations also predicted this T to the minus 503 decline in intensity, which are published in Perlman's paper, Eric Perlman. And there's also suspicion that we have another one in NGC 660, but we just don't have enough people, manpower to deal with all the data. So that has not been looked into yet. So what you see here, sorry, this is what we call T1, meaning our first observation. And when we fit the data point taking at other observations, you have this flux density decline happening. Okay. Then the magnetic fields. This is my favorite part of them all. There are interesting things happening in the magnetic fields that we did not expect. Like seriously, in the beginning, we didn't even know if we were going to be able to detect the magnetic fields to the extent that we did. So we're really happy about these results. So using something called rotation measure synthesis technique, where you take advantage of your wideband field, you divide up your data into channels that correspond to different bins of frequency, you're able to look more into what is happening with your magnetic fields in depth, not just on the plane of the sky. So this image to the right here, it's a composite image of galaxy NGC 4631, also called the wave galaxy. And it's revealing that we have large magnetic structures here. The colors are the results of the rotation measure synthesis technique and show that the magnetic fields are reversing in direction. So this is the very first time that this has ever been seen in another galaxy. So we have large-scale coherent magnetic field reversals in the northern halo that show up like ropes with alternating directions, and these are on kiloparsec scales. So the maintained theory, or the theory we agree on currently on how magnetic fields in the disk are generated, is something called the dynamo model, dynamo action, where spiraling magnetic fields are produced in the disk, and then they continue out spiraling into the halo, which is the continuation of the normal spiral arms in the galaxy disk as well. And these ropes, they spiral far outward in the form of giant magnetic ropes that are perpendicular to the disk. And we can notice that in other pictures I have later on, that it's parallel. When you're close to the disk, your magnetic field lines are parallel to the disk, and then they kind of turn upwards. There we go. So what about the X shape of the magnetic fields in the galaxy? So magnetic field, as I mentioned, magnetic fields in spiral galaxies have large-scale spiral structure along the disk, but is turning X-shaped in the halo of some galaxies. This has been seen before. But the big question is here, how prevalent is the X-shape? Is this a normal thing? And is it due to turbulent fields, or is there a large-scale irregular structure going on? And here again, you use rotation measure synthesis. And Marita Krause, who is a member of the CHANG-ES team, she stacked the magnetic field structures of many of our galaxies. Same thing here, we couldn't use all of them for different reasons together. And this is the result of that, where the X, I'm not sure you agree with it as much as I do, but you can kind of see here how the magnetic field lines are stretching out from the center of the galaxy in directions resembling an X, or you'll have to take my word for it. It may be easier to see here in NGC 3044. Here you can barely even see that they are aligned with the disk near the center, but they're just stretching out immediately. So this is the polarization intensity image of this galaxy, and here is the RM synthesis result. And I did promise a few pretty pictures in the abstract, so we'll come to that part right now. This is an NRA image release that visualizes the great extent of the magnetic field, how far away from the disk it can stretch, up to 7 kiloparsecs in this galaxy, which is NGC 4217. This is a radio optical composite optical in the center of this galaxy, and the magnetic field lines are green, as you can imagine. And so I mentioned the dynamo theory, how magnetic fields are generated by the motion of plasma within the disk, but what causes these field lines to stretch so far out in these large vertical extensions, we don't really know yet. And this is what a number of our papers in this project are discussing. And I just wanted to point out that I noticed, if anyone has listened to talks by me and Marie-Lou before, there are these SKA science working groups. And this CHANG-ES image is used here in the cosmic magnetism science working group for the SKA. I was really proud when I noticed this. Now here are two other galaxies. This one is, well, both of these galaxies are rather close to us at about 30 megaparsecs. And so what you see here is great detail in the magnetic field lines on this NGC 5775. It's a Hubble image, the optical, which has in magenta hot knots of ionized gas in like a bubble. These are star-forming region. And they send out these relativistic electrons. Remember I was talking about synchrotron emission in the beginning? That cause these electrons get caught in the magnetic field lines further out and send out your synchrotron emission. And I'd like to mention that the way of displaying magnetic field lines like this is fairly new, and it's called it's using a code called line integral convolution. But it's useful not only because it's very well visualizes the magnetic fields in galaxies, but it's really appealing to the general public as well, which sometimes in radio can be hard. So here is a good example, by the way, of how the magnetic field lines start as semi-parallel to the disk and then curve upwards. And the image to the right is NGC 4666, which is a starburst galaxy. And it has changing directions of magnetic fields within the disk. This one is gravitationally interacting with three other galaxies, two smaller and one dwarf galaxy, which causes starbursts, and presumably is a reason for these stretched out magnetic fields. Now, these two images were actually winners in, it's a few years ago now, it's 2020, but I thought I'd point it out anyways. NRA had a radio contest, so Jan won second prize with this one, and honorable mention with this one. And back then, I did not know Marie-Lou, but she's the one who got the third prize here on this one. So when I picked up these pictures, I thought that was super cool. So I thought I'd mention it. They are well represented within the radio community here. Okay, and her picture was on the Perseus cluster, of course, on jets using STSs and EVLA. And I mentioned the line integral convolution code. Here's just the newest work of NGC 3556, no publications, nothing, so I put the text over here. Just wanted to show you how absolutely intriguing these features are, and I would like to learn more about it. Other results, where am I in time? Okay, I need to finish off pretty soon. You know what, I'm going to go through pretty quickly here. These were actual science goals, vertical scale heights. They are really important to find because you can characterize the halo extent without being limited by sensitivity, not just going to the faintest curve that you can observe, but you have an actual number of what the extent is. And we need this because these are inputs in how to tell us how cosmic rays propagate from the disk out into the halo, which we use, let's see here. Okay, I'm just going to say here that we had one unexpected result in this, that the galaxy size is the strongest correlated with scale height and also with star formation rate. And here is what I want to say. Volker Heersen is the PI of the project currently. He took over after Judith. And he's the guy behind Spinnaker, which is a modeling software, a really powerful modeling software for figuring out how cosmic rays propagate through the disk out into the halo, the winds that make this happen, and if it is via diffusion or advection. And the results from these modelings show that most of our galaxies are experiencing outflowing winds. And in order to be able to do this, we need to separate the continuum emission, what is the thermal and what is the non-thermal. Because I said earlier, we have those two components. Obviously, we're measuring them together. We don't know which is which, or how much rather is from which part. We just know that if there is synchrotron emission, there is magnetic fields. But we need to figure out how much of it is actually due to non-thermal, how much is synchrotron in order to do this model. So this is another main thing of the project. And there's big surveys or investigations doing this using other data. But now, this is Judith, by the way, and yes, we are in Granada. You didn't miss her though, because she had been traveling around Europe to visit many institutes, and when she came here, she just wanted to visit me, and see Granada. But that didn't stop us from going through her latest project, which is using the new S-band data to solve the division between thermal and non-thermal emission. So this is going to be quick, I promise. The new S-band observations, this is what we're calling CHANG-ES 2. Just a few years ago, the VLA was equipped with S-band correlated receivers, and our team perked up. What can we do with this? Well, we knew what we could do with this because we had, as a result, seen that in L-band, we had little or no observed polarization, and in C-band, we had a fair amount of observed polarization. Somewhere in between here is the limit between, it's a transition zone between Faraday thick and Faraday thin regimes, which is filled up by S-band. Okay, so that was our motivation. So we applied for all galaxies except for one, which didn't have any detectable magnetic fields anyways, and successfully observed them during the last 2 years. And here are some of the first results. I'll just show that here. And concentrate on this. The data reduction group, this is a group that I formed during the last year that are concentrating on taking the data from the VLA, but now go through a pipeline. This is excellent because the pipeline makes it possible for you not to have to do all the calibrations that were involved with the Stokes side. However, it doesn't do polarization. So you have to take the pipeline output and figure out how to calibrate it, which is non-trivial. But we figured it out, and so we are using scripts to go through the pipeline output to get the polarization. Here is the result from NGC 3044 for S-band. And when you combine S-band and our old C-band, this is the magnetic field stretching out for NGC 3044. This is the same galaxy I've shown a few times before, and you can just see how much more information we're getting here. I don't really have time for this, but I just wanted to mention that apart from CHANG-ES, there's a CHANG-ES member called, his name is Damas. He was here at the IAA until recently. He actually left maybe a month before I started, but we've known each other for years. He used the CHANG-ES setup to do observations of Higgs and compact groups, the same setups. So we have Higgs and compact groups members in our data reduction group because we use exactly the same methodology to reduce the data. And this is some of the first results. This is a not very good picture of, but it's by design, of Stefan's quintet in optical in the background. And what is exciting here is that we didn't even know if we would get detections, but we have continuum emission here between galaxy members in the group and a lot of magnetic fields. And I don't have time for that, so I'm going to just finish. Well, let me just say that I was very inspired by the Open Science School and took down a lot of notes and noted to my happiness that we have been following reproducibility ideas fairly well throughout the CHANG-ES project. But this is mainly because we did not trust ourselves to remember anything of what we were doing. This was useful though, because for the new S-band data, we needed all this and things had changed. And this is when these concepts become really useful. You need good documentation of what work you've been doing, and having a wiki is indispensable. So this is my summary. There is a number of results so far. There are new S-band data for an in-depth study of magnetic fields, and the results are pending. You've just seen sneak peeks of our data so far. Some VLA nostalgia and a related Amiga project we're working on here at the IEA. And that's what I have to say.
Thank you, Teresa, for this wonderful talk and questions from Teresa. Please.
It's more technical, but you said at the beginning that this project was kind of done in collaboration-ish with NRA. So this was like a large project, or it was shared risk observation?
Yeah, shared risk. Yeah, shared risk, large observing projects.
All of that.
Yeah, all of it, including having to have people come to NRA and stay there. That was me, and develop the strategies for dealing with the data together with them, which was so efficient and really excellent.
So,
Yeah, I have a question concerning NGC 2992. That is an old friend of mine.
Oh, yeah.
Yes. So you said that it was a gene absorptor, or that you could just see the AGN in polarized light.
Depolarization, yes. I was going to put a picture of it there, but I didn't. But I can share with you after the fact.
I remember, I don't know which frequency it was, but I remember quite well that it had radio emission in a period of 8 shape.
Okay.
With a strong point guide source in the center where the AGN is located. So it's not compatible with your saying?
No, it's not. So it is possible that I put the wrong number. I'm going to have to check that.
Okay.
But I'm going to double check for sure.
Interesting talk and nice pictures. I have 2 questions. Could you comment on the depolarization effect at L-band? And second question is this pattern that you see for NGC 5775. Do you see this only for starburst galaxies or also for normal galaxies?
NGC 5775.
Yeah,
That's 3556. Yeah, this one. Well, it's 4666. That's the starburst galaxy. So in this case, well, let me do your first question first. You were talking about the depolarization at L-band.
Yeah.
So the further lower you go in frequency, the more affected you are by Faraday effects and depolarization effects. And exactly what is happening and how and when and at what frequency, that's what we're going to use the S-band data to figure out.
I'm specifically interested at L-band. So do you have any comment on specifically the L-band?
Well, what I can say is that we see polarization at L-band, but to a much lesser extent. So you need to go deeper to even tease it out. And there is depolarization occurring, but I mean, it is different for different galaxies in our samples. So if you are looking at L-band for a compact group, for instance, and I think you might still be seeing some, but it's hard to say. What I should say is you really need to include S-band and higher frequencies as well to get the full picture of what is going on. And what was your second question? Oh, it was about these 5775.
Or saying, like, do you see these kind of patterns only for starburst galaxies or?
We only have a few starburst galaxies in our sample. Not all are as close as these ones. and we have 35 galaxies in the sample. So I can't say just general for all galaxies. These are what we see in some of them, is what I've been showing. We still have to do a lot of, you know, I showed you the list of all the papers. There's so much more still to do. And I just showed you a few results from all these papers. And it was so hard to choose which ones to show. In the end, I just went with the ones with pretty pictures, but because they were also the coolest. But the rest are as well, and some are really important but hard to describe, like the cosmic ray propagation, the winds, and so on. I kind of really glossed over that slide here. And so, in other words, there's just so much still to learn from these data.
More questions? Anyone in Zoom who want to make a question to Teresa? Sure.
So I don't know anything about those halos. So, but in the end, they are in all galaxies or only spiral galaxies, or what's in those 35? Like what do you guys see?
What we know is that they are more prevalent in spiral galaxies than we previously thought.
Okay.
We have not studied non-spiral galaxies.
Yeah, but you detect them in all of them.
You do, yeah, you do need some kind of source for cosmic rays to be sent out to get the detections at relativistic speeds. And yeah.
I have another questions. Do you know the effect of the magnetic field on the ability of the gas to escape the halo?
Effect of the magnetic field on the what?
Ability of the gas to escape the halo.
This is one of our questions. It's a very good one. I can't say an answer to that. It is possible some of our members have looked into it, but I think this is still being looked into. There is, I should point out, there is in particular a really good paper come out from this survey by Marita Krause 2019, I think, that goes through all the galaxies and RM synthesis and magnetic fields for them. That's the one where they had the stacked image of the X shape. That's just a minor result from her paper. That is definitely useful to look at.
More questions? Okay.
Awesome questions.
No one here at Zoom. So thank you, Teresa, again for this.